We received an email from a lovely young woman named Adriana recently, who shared with us that her boyfriend Jorge is a huge fan of the Being an Engineer podcast, and asked if it would be possible to send him a short message as a surprise for their upcoming anniversary. So, Jorge, thank you so much for your support, and from all of us here at the podcast, we wish you a wonderfully memorable upcoming anniversary. And hold on to that Adriana. She seems like a keeper. Hello and welcome to another episode of the Being an Engineer podcast. Today we're speaking with Yonatan Cohen, who holds bachelor's, master's, and PhD degrees in physics. Yonatan is co-founder and CTO at Quantum Machines, where they're a team of quantum physicists, software and systems engineers, and chip designers are on a mission to advance the world of quantum computing. Yonatan, thank you so much for being with us today.
Thank you for having me. I'm very excited to be here.
All right. Well, what made you decide to become a physicist?
I kind of always had, when I was like a young kid, I had kind of like two main interests. One was like how computers work, so why do I see those things on my screen, on my computer screen? How do I see images and characters and moving when I press different keys? And the other one was the same, but about the universe, kind of, why do I see things around me, and how does it all work? And then when I was in high school, I took classes in both physics and computer engineering, and I felt that I got it in terms of how a computer works, but not how the universe works. So I continued with physics. Yeah.
Well, it sounds like you were a deep thinker from an early age.
Yeah, just curious about stuff.
Yeah. Well, tell us a little bit about quantum computing. I mean, I think we have all heard the term quantum computing at this point, but I think a lot of us really don't understand what it is. So what is quantum computing, and can you explain a little bit, basics, how does it work at a fundamental level?
Sure. In general, the quantum theory of nature kind of expands the very basic way in which how we understand nature to be working. So, and one of the fundamental aspects of it is that things, especially when we talk about very small things like electrons and atoms and things like that, they are not really in one state or the other, like we know from classical physics, right? Like if I hold a coffee cup in my hand, it's only in my right hand. It's not in my left hand, right? So, and it's definitely not on the table when I lift it up, right? But it turns out that when you go to like what we call quantum systems, but this is just, every system, but we see it when we isolate tiny particles from their environment, we actually see that they can be in multiple states at the same time. We see that an electron is in two different places at the same time, which is very weird, but it happens. And we have a mathematical framework to describe that and to calculate results of experiments that we do with those electrons or atoms or other quantum systems. And that's quantum physics. And then, in the very late 70s, early 80s, physicists started to ask, can we build a computer that's based on these fundamental expansions of nature? Because a classical computer, a regular computer, is based on the fact that systems could be in the system, like even the full computer, it can be in one state at every point in time, right? All the different bits in my memory, they encode a single state, like 0, 0, 0, 1, 0, 1, 1, 1, 1, 0. Okay, so whatever it is, it's just a single state. But physicists started to ask, okay, maybe I can use the fact that I can build systems that can be in multiple states at the same time, and that's a quantum computer. it's a computer that's based on these quantum systems, and the fundamental building block is called a qubit, because instead of a bit, which is the fundamental building block of a computer, that's a system that just has two states, 0 and 1, and it can be in either 0 or 1. A quantum bit or a qubit can be in both 0 and 1 at the same time. And so a quantum computer is built out of these like many qubits that can be in many different states at the same time. And so in certain problems that we want to solve, this can allow us to sort of parallelize the computation so that we can gain a computational advantage. And that's
okay. Let's go back to the states just real quick here. When you use the word state in the context of quantum physics, is that referring to a location? Is that essentially what the state means? Different physical locations?
It's a great question. I mean, it doesn't have to be a location. In elementary, physics, we typically look at a position of a particle, but it doesn't have to be. It could be, for example, we now know how to build qubits, for example, from what's called superconducting circuits. And there you can build a circuit, you can build a tiny loop from material called aluminum. It's regular aluminum. When you cool it down to very low temperature, it becomes quantum. It actually becomes superconducting. And then the current in the loop can flow clockwise or counterclockwise. Okay, but it can also flow in both counterclockwise and clockwise. So
interesting.
Yeah. So the states are the direction of the current, for example, in this specific system. Another system that we use to make qubits is called a spin qubit. So there is a property for certain particles that's called spin. It's like an arrow that can point up or down, but it's quantum, so it can point up and down at the same time. Okay.
Okay.
You can kind of think about it as the particle like kind of spins around itself, so it can spin again clockwise or counterclockwise. It's not really what's happening, but that's a way to visualize it. But it's those states are abstract states in which the system the system could be in. So whatever different configurations that the system can assume, that's what we call states in physics.
Okay, I see. That's helpful. Thank you for explaining that. So in quantum physics, a particle can be in multiple states at the same time. Is it just two states? A particle can be in one state or another or both? Or are there situations where particles can be in like 3 states or 4 states or 20 states?
Yeah, exactly. So they can be in all the states. So classical physics basically says, I'm sorry, I'm going back again to classical physics just for a second, but classical physics basically says the following. Take a system, it has many states called the state, the phase space of all the different states that the system can be in. Again, it can be position, it can be other things that we know that exist in nature. But the system at every point in time is in a single state, and then we have what's called the equations of motion, right? This is what's basically, these are the rules according to which the system moves from one state to another, right? From, if I throw the coffee cup that I hold it in my hand on the wall, it will start moving from one position to another at every point in time, according to the equations of motion, the Newton's equations and so on. In quantum, the main expansion is that we say, it actually is in all states of all possible states at the same time. And what's changing are just the weights of these states, like meaning how much am I in this state or the other.
Oh, that's mind blowing, right? I mean,
yes. And by the way, this is also the same with the computer, right? Because when we have a classical computer, it's made out of bits. Each bit can be either 0 or 1. So when you take 2 bits, you already have 4 states, right? 0, 0, 0, 1, 1, 0, 1, 1. And if you have 8 bits, you have 256 states. And in a computer, of course, you have billions of bits. So you have bajillion states, okay? But at every point in time, the computer is only in one state. And every clock cycle of the computer has a clock. And every clock cycle, we're moving from one state to another. And that's how every algorithm essentially works, like a state machine. We go from state to state to state to state until we reach a final state that is the solution to a problem. A quantum computer, and that's like the equation of motion. We program the equations of motion to solve a problem. Like we program the how we want the system to move from state to state. And with a quantum computer, we have, instead of bits, we have quantum bits. So again, we have many states, 000, 001, 010, all these states. But we are in all of those states at the same time, and we just program sort of how we move, how the weights of these different states, meaning how much am I in the 000 state, how much am I in the 001 state, etc. How it's changing with time.
Is it accurate to say then that processing on a quantum computer happens more in parallel rather than in series, since the qubits can be in all these different states at the same time?
Yes, it's accurate, but there is a catch, which
okay.
And that catch, in most popular kind of talks or articles, people don't talk about it. Just say, okay, everything runs in parallel. But it's true that everything runs in parallel, but there is a catch, because at the end you also end up with all the results in parallel, which is not what.
Oh,
right? It's not really what we want, and so it's not as easy to win with a quantum computer as just saying, "Oh, I'm just trying everything in parallel." You know, like a classical computer would have to scan all the different solutions, right? Go in this path, then go in this path, then go in this path. But a quantum computer just goes in all paths together. It's true that it goes in all paths together, but it ends up with all the results. So the way around this problem is to use what we call interference. And what this is, it's so these numbers that I told you about, these weights, like how much am I in 000, how much am I in 001, etc. These are actually not just positive numbers. These are actually complex numbers. So there can be negative. I can be a little bit in 000, I can be a lot in 001, and I can be minus in 010.
Okay.
And this is important because as I evolve the state, these numbers can, as I go in all these different computational paths, at the end, some solutions, the paths that are leading to some solutions will add together, and paths that lead to other solutions will cancel one another. Okay, just like you can think about it like kind of like waves in the ocean interfere, right? So in some places in the ocean, two waves come together and they make a large wave, and in other places in the ocean, two waves come together and they make, a flat wave because they hit each other.
Mm-hmm.
So exactly the same happens with parallel computational path in a quantum computer. And so if you design the quantum algorithm right, and also it doesn't work for every problem, it works for specific problems where we actually know how to design the right algorithm for, then the parallel path leading to the right solution to the problem interfere what we call constructively. They create a large probability at the end to measure this specific state that is the right result, while all the other paths leading to the wrong results, they cancel one another.
Okay. Conceptually, I understand what you're saying. That is fascinating. I think you mentioned that quantum computing was theorized in the 70s. At what point was the first quantum computer actually built and used?
So the first thing that you could call a quantum computer, I would say, was built in 1995, and that was the simplest quantum computer that you can build. It's made of 2 qubits, where you can actually make an operation between those 2 qubits. Because you can have a single qubit people had before that, but unless you can show that you have 2 qubits and you can entangle them, meaning you can form an operation that will make them be in a superposition of their combined states that you cannot reach without having them interact with one another, then you don't really have a universal quantum computer. So the first time people built a universal quantum computer was in 1995 with trapped ions. So that was a major achievement. And since then, things have improved a lot, and we're now at hundreds of qubits. So
wow. What does a quantum computer look like? I mean, is it completely different than, the typical PC that we use now? What are some of the core components inside a quantum computer?
Yeah, so they look very different today. Maybe it will change one day, but right now, to begin with, they're very large. They're very still kind of looking like almost like computers used to look when 60 years ago, okay, or even more.
Yeah.
So it looks like a lab because it still is a lab in some sense. So there are many different ways to implement qubits. So depending on how you implement your qubits, your quantum computer is going to look very different. If you're implementing your qubits using superconducting qubits, this is what most of the big companies like IBM, Google, AWS are doing. Then the qubits sit on a chip. So in this sense, it looks similar to a regular chip, but this chip needs to be cooled down to extremely low temperatures. So what you typically see if you Google a quantum computer, you typically see a refrigerator. The inside of a refrigerator. It's a very cool refrigerator. It looks very neat. It looks like a chandelier or something. And if you Google it, you'll see it. And that's actually the cooling system to cool down those chips to temperatures that are close to absolute zero, so that chip actually behaves in a quantum manner when we do that. That's one way that the quantum computer looks like. The other way, if you make your qubits from ions or atoms, then typically you would have a vacuum chamber in which you have the ions or atoms trapped in it and sort of trapped in a vacuum with lasers. And around that vacuum chamber, you'll have tons of lasers and mirrors and all kinds of optical equipment that is used to send the laser beams to the ions or atoms to control them, to perform the operations on them. So these are kind of the two main examples for how a quantum computer would look like. Either it's a fridge or it's a vacuum chamber surrounded by mirrors and optical components.
Okay. Pretty big. This is filling up like a room kind of, huh?
Yes, it's filling up a room. Typically, besides the core quantum system and these like surrounding electronics, there's also what we call the control system. That's a system that's responsible to generate the signals that will go to the qubits and operate them. That's what actually we are focused at Quantum Machines. We're building that control system that orchestrates all the signals that need to go to the qubits and tell them what to do. So that's kind of like, I don't know, racks of electronic equipment that is used to do that. So that's another piece.
Let me ask you about the temperature here. Why is it that these systems need to be so super cool down to almost absolute zero temperature in order to work? What's the relationship between the temperature and the functionality of a quantum system?
Yeah, so it depends again on your qubit. Typically, the way you implement the qubit is, again, we want a system that has two states, 0 and 1, and it can be isolated from its environment, and it behaves quantum mechanically. So typically what we do is we pick a system that has two energy levels and two energy states, and those states are separated by some energy. So think about an ion or an atom. It will be the orbits, the orbitals of what you learn, in high school chemistry when you see the orbitals, right? The electron is kind of orbiting around the atom, but it can orbit, close to the atom or to the nuclei, or it can orbit farther away from the nucleus, but it can only orbit in certain orbitals that are quantum mechanical states, actually, that are separated by some energy gap. And this, depending on the size of the energy gap, the temperature could make you go from one state to another unwantedly.
Okay.
So you need to cool down this. So with superconducting qubits and semiconducting qubits, we are actually not using the orbitals of an atom or ion, which are kind of far away in energy, but we are sort of engineering a system, like I told you before, like these loops of aluminum where the current can flow clockwise or counterclockwise. These are separated by a relatively small energy gap that at room temperature we will just not be able to separate. So it will just look like like a classical system. We won't be able to separate the quantum states. So we need to cool it down to extremely low temperatures in which we can actually see the quantum behavior, so that the temperature is much less than the energy gap of the quantum states.
Okay, so you're controlling for, I guess, reliability. You wouldn't be able to predict the energy state of the electrons orbiting around the atom if the temperature wasn't super cooled down to almost absolute zero. Is that accurate to say?
Yes, and once the temperature starts kicking your system from one state to another, you basically lose its quantum mechanical nature. You cannot. Yeah.
All right. So you're keeping the electron in that close energy state. The qubits that we've been talking about, is a qubit a physical thing? I mean, if you had an electron microscope, could you see a qubit, or is this it's just an abstract term we use to describe some phenomenon that's occurring?
No, so I mean, again, it really depends on the qubit. But with superconducting qubits, they're pretty bulky, they're pretty large. You can see them with your eye. You might not be able to see the critical element that makes it, a good qubit, but you see the structure in your eye.
Interesting. Okay.
With ions, of course, you cannot see an ion with the naked eye, but you can see it with a good camera. For example, you can take a picture of an ion. You can see beautiful pictures of a string of ions trapped in vacuum chamber. But yeah, it's a physical thing. The actual quantum properties, these are more abstract things, like the spin of the electron or in which orbital it is in the ion. That's not something you can see with your eye. You need to do something in order to detect it, like shoot a laser beam at it, and then pick up the lights with the camera or with single photon detectors in order to distinguish whether the electron was in this orbital or the other, and make a measurement of the qubit.
I see. Okay. How much faster is quantum computing than, your typical PC or Mac? And, how is it measured? We use like processor speed and,
That's a great question. So in some sense, it's much, much slower than a classical computer, right? And I mean in the sense of how many operations can you do in a second on a quantum computer? Today, at least, you can do far less in terms of the number of operations that you do per second than you could do with your computer. So even in superconducting qubits, which is the fastest, what we call gate time or operation time, the operation takes, let's say, about 10 nanoseconds. Okay, 10 nanoseconds. Whereas in a modern computer, a single operation in the CPU takes less than a nanosecond. So that's a factor of more than 10 for an operation. And that's the fastest quantum computers. But as we said earlier, it's when we talk about solving certain problems where, well, then the situation is different, because it's not just about how many operations we can do per second, because each operation now takes us to a parallel, to two parallel worlds, right? So we are parallelizing the computation. So a quantum operation doesn't just take the system from one state to another, but maybe it splits it to two further more systems and so on, right? So that's what we really are using in a quantum computer to get an advantage. And in problems where we have algorithms that can gain from this parallelism, then in theory, when we have a large enough quantum computers, it's not going to be a match. So a quantum computer could solve certain problems in minutes or seconds, problems that would take on a crazy supercomputer, billions of years. Okay, so that's
wow.
But this is again just in theory. We don't have a quantum computer that does that today. Well, there is a proof of concept for that. So Google was the first one to show something like that, where this was called quantum supremacy. Nowadays, it's not politically correct to say supremacy anymore. So, but this was a demonstration where they show that there is a problem. It's not a useful problem. It's not helping anyone today solving real world problems, but it's a problem that you can define it well. And they solve it with their 54 qubit quantum computer much, much faster than you could solve it on a supercomputer, even the largest supercomputer on Earth today. And that was sort of a very important milestone for quantum computing, because that showed that the concept works.
Right. Yeah. Okay.
Not yet for very interesting problems, and that we hope will happen in the next few years.
I'm going to take just a real quick break here and share with the listeners that teampipeline.us is where you can learn more about how we help medical device and other product engineering or manufacturing teams develop turnkey equipment, custom fixtures, and automated machines to characterize, inspect, assemble, manufacture, and perform verification testing on your devices. We're speaking with Yonatan Cohen today. So, Yonatan, you were just mentioning that in some ways, as far as the operational speed, quantum computers are actually slower than your typical PC or Mac computer, but because it can perform operations in parallel. I guess it sounds like it's all about finding the right application for the quantum computer. Is that an accurate statement?
Yes, definitely. Today, that's one side of it, and the other side is to build a machine, to build a more robust machine, because today's quantum computers are still very first of all, they're still very small. We're at about 100 qubit now. Well, IBM just came out with a 400 qubit computer, but that's by far the largest that was announced. Most of the industry is around 50 or maybe close to 100, and these are still very small quantum computers, and they're very noisy. So the error rate is very, very large. So one huge effort is to build larger quantum computers and more robust, with much less noise quantum computers. And the other effort is, to find, even for those small quantum computers, what application, because we know when we build a large quantum computers without errors, we already have a few applications that are going to be, very disruptive. But today, a lot of the game is to find those applications that even with, maybe several hundreds of qubits or maybe 1,000 qubits would already give an advantage in interesting problems. So yes, it's about finding those first applications.
What are some of those applications that once we get to that point, we can be disruptive with quantum computing technology?
Yeah, so let me start with the with the very long term. If we had a very large scale, I'm talking about millions of qubits quantum computer that and where we don't also have errors, this is what's called a fault tolerant quantum computer. Like a classical computer, you have actually billions of bits, not millions, and when you run a computation, you run it almost always without errors. Okay, once in a while you have a blue screen of death because some crazy cosmic ray hit your SSD, and created a bit flip. But that's super rare. And typically you run a full application without any errors at all. So if we had a quantum computer with millions of qubits and no errors, something that will take some time to build, then I would say the sort of killer app, almost literally, is what's called the Shor's algorithm. And that algorithm essentially can break all encryption on the internet today. Okay, so
interesting.
Yes, it can factorizes large numbers into their prime factors very quickly, and what's called the RSA protocol for encryption is based on this problem that classical computers cannot factorize large numbers into their prime factors very quickly. We know how to do it only exponentially today, in the size of exponentially. The time that it takes to solve the problem is exponential in the size of the number that we're trying to factorize with classical computers. So that's a problem where if we had a large-scale quantum computer, would have disrupt dramatically the world, in fact.
So that brings up an interesting question. If quantum computing could effectively break all of the encryptions that are being used out there, probably military-grade encryptions as well, are there groups out there who are opposed to the idea of developing quantum computers because of what it would mean for lack of a better term, cybersecurity?
I don't know if people are opposing it as much as they are in favor because they're afraid that the other side will get it, right? So that's, kind of, it became very strategic also for countries and big companies, big enterprise companies to basically to put a lot of investment in that because of this one application. Because you cannot afford not being in this game. Because currently this is, as I said, that's why I call it the killer app for quantum computers still. I think it's one reason why people put a lot of effort into building those machines. But there are other applications, and the other applications I would say are, maybe less frightening. And there's no reason to be worried too soon. I mean, we're now, as I said, we're at 100 qubits. It's going to take a very long time until we build a million qubits computer. And again, without errors. The errors are actually harder than to just scale up the computer. So actually, the much smaller number of qubits, we think that things like computational chemistry and quantum simulations, as well as perhaps some optimization problems, general optimization problems that could be relevant to many things like network optimization or logistic optimization, risk portfolio optimization, things like that. And again, chemistry problems like simulating certain molecules, how they interact, their ground states, and so on, for whether it's drug discovery or whether it's material design, things like that. These are things where we think, but we don't have a proof for many of them. For some of them, there are starting to be proof, but for many of them, we don't have proof. We just have a heuristic algorithms for which we need to build a few hundreds to a few thousand qubit machines and just run those algorithms and see if we get the expected advantage against classical computers.
Right, right. So is quantum computing being used, I mean, commercially for anything today, or is it really still in its infancy and just kind of experimental for now?
So it's pretty much the second. It's still being developed, and but I would say that there are starting to be very, very narrow applications, like scientific research by itself is already starting to. So, you can say I like to say that the first quantum computers, all you could do with them is to explore themselves. They could explore themselves. So you build a qubit and you see if it behaves right, if it's a real qubit, if it behaves according to theory. You build 10 qubits. You see if your quantum computers works basically, and how much you can push it to behave like a theoretical perfect quantum computer, and so on, and then optimize it and so on. So it's exploring itself. What we can do now is we can start exploring with the current quantum computers other quantum systems. Where the first such so because you can simulate another quantum system with your quantum computer, and that's actually super efficient. That's that is, I think, one of the first applications, and that is actually was the first motivation to suggest. Richard Feynman, that was one of the first people who suggested to build a quantum computer, did it for that reason. He said, we cannot simulate quantum physics with classical computers. Why don't we just build a quantum system that can simulate other quantum systems? And that's already an interesting application in my mind, because the people who do that, maybe it's not the general public, but people who try to simulate quantum physics, typically, and they're not that, the efforts are not that little, surprisingly. They go to huge clusters and HPC, high performance computers, supercomputers, to do that, and it's very inefficient. It costs a lot of money. And it takes a lot of time. And if you could just simulate the quantum system that you want on your quantum computer, that's already very efficient. So that kind of, to me, is the first application. And there's starting to be already papers on other quantum systems that are being simulated with current quantum computers. I think that what will happen is that from this, just simulating quantum system, because it's an interesting scientific question that we want to solve, to now simulating quantum system to design a molecule that can actually cure disease or be a catalyzer in an important chemical reaction to create energy or to make solar cells. And once this happens, then it's already starting to become relevant, not just to science, but also to industry, where we're simulating quantum systems that are now relevant to the industry. And
at that point, do you think that starts to fundamentally change the world around us? I mean, fundamentally change things like transportation, the food that we eat. You already mentioned medicine, but how dramatically does the world change once quantum computing is part of our everyday commercial industrial practice?
So that's it's very hard to predict the future and not to be to try to predict the future and then not to be wrong. So
sure. We'll take this with a grain of salt.
Yeah, but I think slowly, it will start changing certain industries, and then more and more and more, and hopefully. Yeah, I think there is a potential to disrupt many fields and many industries. We're solving hard problems that are today sort of out of reach from classical computers. Again, in some of these cases, we don't know for sure. It's kind of like, neural networks is a good example, because nobody knew. There were no proofs for some of the neural networks. Why? Until today, we don't know why some of those neural networks work so well, right? There's just no explanation. So with quantum computers, we do have some algorithms, like the Shor algorithm that I mentioned, that which we understand actually why it works so well. But then there are also many algorithms that are relevant to optimizations, to machine learning, to neural networks, and to computational chemistry that we don't have full proof. So we just need to sort of build those machines. I believe that once we build those, we will discover where they are really powerful, and I think that this will disrupt at least certain industries dramatically. But it will take some time, because building these machines is a very hard engineering problem.
Yeah. Again, I'm asking you to predict something, so certainly no one's going to hold you to this, but best guess, I mean, how far away are we from having one of these quantum computers that has, 1 million qubits? Is this 5 years? Is it 50 years? Is it 150 years away?
I think that in the next decade, we will probably stay with, up to 10,000 qubits. I mean, in the next few years, we will reach 1,000 qubit computer. And then in the next few years after that, I hope that we will scale up by another order of magnitude. From there, I find it hard to predict.
Mm-hmm.
But I think that in those numbers, we're already going to see applications, interesting applications. So already we're going to see a massive change in the field from, a field that, generates a lot of interest and a lot of money goes into it also, again, because there are some known applications, to a field that's already generating, solving hard problems that cannot be solved without a quantum computer, to people that were this problem. So I hope that in the next 5-6 years, we will see those first applications that are actually money generating, so that the field kind of starts to really explode. And I think that's going to be a turning point, because you see, with classical computers, like, people always talk about Moore's law, right? We scale, we double our computational power every couple of years, and that's crazy. But it's actually also true that in order to keep up with Moore's law, the amount of resources to research and development of classical computers that had to be invested every year in order to continue to scale classical computing like that was also exponential. So in order for quantum computers to make it, we also need more and more and more resources to continue to go into the field. And that's why it's so important that in the next several years, we have an application. It doesn't have to, disrupt all of the industries, all of the fields, but it needs to be a real application. And then like a first real application to justify bringing more and more and more resources into the field.
Yeah, that makes sense.
Because we're competing with the most powerful machines and the biggest achievements that humankind have achieved so far, which is classical computers.
Right. Yeah, no pressure. Okay.
Yeah.
Well, let's see. Just maybe one more question, and then we'll wrap this up. Can you tell us a little bit about the quantum orchestration platform that your company has developed? What's that about?
Of course, I was waiting for this. Yeah. So this is this is our product at Quantum Machines. We develop what we call the quantum orchestration platform. So really quickly on the implement, like very, very high level, a quantum computer is built out of 3 layers. So whereas a classical computer has 2 main layers, right? There's hardware and there is software. In quantum computers, we have 3 layers. We have quantum hardware, classical hardware, and classical software. The classical hardware is also called the control system, and that's what we call the quantum orchestration platform. And that is the system that's responsible to receive from software what it is that you want to do with your QPU, your quantum processor, your quantum hardware, and it translates it to an orchestra of signals, typically RF signals, that needs to be sent to the quantum processor and also needs to be read out, signals that return from the quantum processor, in order to perform the quantum algorithm. So that's the control system or the quantum orchestration platform. That's what we develop at Quantum Machines.
Okay. So would the idea be that organizations out there who are trying to develop their own quantum computers would use your control system, the orchestration platform?
Yes, we're working with many of the organizations, many of the companies, startup companies, big companies, academic labs, national labs that are developing these quantum computers, and they buy from us the quantum orchestration platform and build their full stack quantum computer on top of it.
Got it. Okay. All right. That makes sense. Well, great. Yonatan, is there anything else that you think we should talk about that we haven't discussed yet?
No, if you're interested in learning more about the field or going into the field, then please reach out. And
how can people get a hold of you?
Write me on LinkedIn, send an email through our website. I think probably LinkedIn is the best choice.
Okay, perfect. And we'll certainly have a link to your LinkedIn profile and also your company website in the show notes here.
All right, perfect.
All right. Well, Yonatan, thank you so much. This has been super interesting, just mind-blowing stuff. Very, very exciting to see where this field heads in the next, 5-10 years. Like you mentioned, probably start to see some real world applications taking off. So thank you so much for being with us today.
Thank you, Aaron. It was a pleasure.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.